On a Boeing 777, most overhead luggage bins look identical. Same plastic shell, same chrome latch, same hinged door for your carry-on. But on certain rows, usually near the forward or rear galley, one bin is different. It has no latch and it doesn't open. That's because it isn't a luggage bin. It's a trapdoor, and directly above it, separated from the passenger cabin by a few inches of ceiling panel, is a fully functioning bedroom. Beds, seat belts, independent climate control, its own oxygen supply, a space built to keep humans alive and asleep at 35,000 feet, suspended in the gap between the top of the cabin and the outer skin of the aircraft. Most passengers fly directly beneath it without ever knowing it's there, and the engineering required to put it there is far stranger than just building a room. Here's what you can actually observe from your seat, if you know where to look. On a modern widebody, a 777, a 787, an Airbus A350, there's a door near the forward or aft galley that looks like a utility closet. Small digital keypad, no window, no signage. Crew members occasionally punch in a code, slip through, and disappear for hours. If you're seated in certain center rows, you might notice the ceiling is slightly lower than the rest of the cabin, a subtle downward bulge where overhead bins should be. In some rows, the center bins are missing entirely. The airline didn't forget to install them. They were removed to make room for what's above. Most passengers assume the crew sleeps in empty seats somewhere in the back, maybe behind a curtain. On older aircraft, that's exactly what happens. Blocked-off economy seats with heavy drapes pulled around them. And on the double-decker A380, the crew actually does sleep below the cabin floor, in modules nestled among the cargo containers. But on single-deck wide-bodies, the 777, the 787, the A350, the cargo hold is full of revenue-generating freight, and the main deck is monetized to the last seat. The only unclaimed space is above, which, from the passenger's perspective, seems impossible. The ceiling looks like a thin, continuous panel, maybe a few inches thick. But the fuselage of a wide body is circular, and the passenger cabin inside it is flat-topped. Between the highest point of that flat ceiling and the curved outer skin of the aircraft, there are several feet of empty space, a void originally designed to route wiring and air ducts. Engineers looked at that void and saw a bedroom. For a flight like United's 17.5-hour non-stop from Houston to Sydney, a curtained seat isn't close to adequate. Federal regulations require a flatbed, sound isolation, and independent temperature control, formally classified as a Class 1 rest facility. On these aircraft, that facility is directly above the passengers' heads. Behind that locked door is a staircase. Narrow, steep, almost ladder-like, it occupies roughly the same footprint as a single aircraft lavatory. At the top, it opens into a space most passengers would never guess could exist inside the airplane they're sitting in. The compartment is tight. Ceiling height barely clears 5.5 feet. Bunks are stacked in rows, typically 2 for pilots, up to 6 for cabin crew, each one roughly the dimensions of a standard twin mattress. 78 inches long, 30 inches wide. The volume per sleeping space is about 1 cubic meter, approximately the interior of a large household refrigerator. You don't step into these bunks, you slide in. But the engineering holding this space together goes far deeper than foam and fabric. The module isn't bolted to the cabin ceiling the way a shelf mounts to a wall. It's suspended from the aircraft's primary fuselage frames, the structural ribs of the airplane, using a network of tie rods and vibration-dampening isolator brackets. The upper fuselage is one of the noisiest zones on the aircraft. High-frequency vibrations from airflow over the skin converge in the crown, and if the module were rigidly attached, it would act like an acoustic amplifier, buzzing and rattling constantly. The isolators physically decouple the pod from the airframe, creating something closer to a floating capsule. Crew members report that the inside actually feels smoother and quieter than the passenger cabin below. The acoustic target is 70 to 75 decibels, roughly the noise level of a running shower. That takes serious engineering, because on the other side of the fuselage skin, the aerodynamic roar exceeds 100 decibels, closer to a chainsaw at arm's length. The material that makes the structure possible is not what most people would guess. The floors, walls, and load-bearing panels are built from Nomex honeycomb, an aramid polymer, a chemical cousin of Kevlar, formed into a hexagonal pattern and sandwiched between thin composite sheets. The result is a panel that provides enormous rigidity, where it needs to bear weight while being mostly air by volume. A complete overhead rest module on an A350 weighs about 580 pounds, roughly the same as an upright piano. An equivalent module built for the lower cargo hold using conventional materials would weigh nearly 3 times that. The honeycomb is what makes it light enough to hang from the ceiling without shifting the aircraft's center of gravity beyond its limits. Each bunk comes with a seatbelt. That detail surprises people, a restraint for sleeping. But at cruising altitude, clear air turbulence can drop an aircraft 100 feet in under a second, and a sleeping crew member without a belt would be launched into the ceiling of the pod, which sits inches above their face. Sleeping unbuckled at 35,000 feet isn't just dangerous, it's a federal violation. The air inside the pod is controlled independently from the passenger cabin. A dedicated branch of the aircraft's environmental control system feeds conditioned air directly into the compartment. But the crew gets something passengers don't. At cruising altitude, cabin humidity drops below 2%, drier than the Sahara. Breathing that air for hours degrades sleep quality, dries out your throat and sinuses, and weakens the immune system, which directly increases fatigue. So the crew rest has a dedicated humidifier built into its air supply, artificially raising the moisture to a level that supports genuinely restorative sleep. Temperature is adjustable from a panel inside the pod, anywhere from 59 to 79 degrees Fahrenheit, completely independent of whatever the main cabin is set to. The crew is breathing different air than you are. Fire is handled separately from the rest of the aircraft. The compartment has its own smoke detection system, with sensors that trigger alarms simultaneously inside the pod on the flight deck and in the passenger cabin. If smoke is detected, the system automatically shuts off the fresh air supply to the module, starving a fire of oxygen before it can spread to the wiring bundles routed through the crown. And because standard chemical oxygen generators, the kind behind passenger drop-down masks, burn at over 500 degrees Fahrenheit during activation, they're banned from the crew rest entirely. The oxygen supply instead comes from the aircraft's centralized gaseous system, the same one feeding the flight deck. The device designed to save your life in an emergency burns hot enough to start one. So, in a fabric-lined pod in the ceiling, it was the first thing engineers removed. Then there's the escape route. If a fire breaks out in the galley below and blocks the primary staircase, the crew above is trapped in the ceiling of a burning airplane. Engineers solve this by building a secondary exit into the floor of the compartment. A crew member pulls a release handle, a floor panel drops open, and the bottom of what appears to be a standard overhead luggage bin falls away from the passenger side, revealing a folding ladder that extends directly into the aisle. The bin with no latch, the one that looked broken or incomplete from below, was never designed to hold luggage. It's an emergency exit from a room most passengers never knew existed. Every crew member briefed on that aircraft knows exactly which bin it is, but all of that assumes the flight goes normally. The most dangerous scenario the compartment has to survive is the one where it doesn't, and the engineering response is the opposite of what anyone would expect. If you want the next one of these to show up automatically, subscribing takes 1 second. The scenario is rapid decompression. If the fuselage is breached at cruising altitude, a window fails, a section of skin ruptures, the pressurized air inside the cabin evacuates violently. The pressure drops in seconds. Every space connected to the cabin equalizes almost instantly. But the crew rest, sealed behind its locked door and composite walls, doesn't equalize on its own. The trapped high-pressure air has nowhere to go. Within fractions of a second, the pressure differential builds to thousands of pounds of force acting on the module's floor and walls. If the walls hold, the floor could blow downward into the passenger cabin. If the floor holds, the walls could rupture outward into the crown, severing flight control cables routed through that space. The intuitive response would be to build the pod stronger, reinforce the walls, thicken the floor, make it rigid enough to contain the pressure. That would be the worst possible solution. Instead, the crew rest is built with blowout panels, calibrated weak points integrated into the base of the module. Spring-loaded grills or shear pin latches engineered to fail instantly at a specific pressure differential of roughly half a pound per square inch. When decompression hits, the panels snap open in milliseconds, venting the trapped air downward before the force can build high enough to damage anything structural. The pod doesn't survive because it's strong enough to contain the pressure. It survives because it's engineered to give way instantly. The deliberate weakness is the protection. The reason engineers put a survival pod in the ceiling, instead of claiming space on the main deck or in the cargo hold, comes down to the variable that shapes nearly every design decision in commercial aviation: revenue per square foot. Every passenger seat generates ticket income. Every cargo container in the belly generates freight income. The overhead crew rest displaces neither. By engineering a habitable pod into dead space that would otherwise hold nothing but wiring and ductwork, airlines preserve the equivalent of 16 or more passenger seats and at least one full cargo pallet on every flight. Over a 20-year service life, that single architectural decision generates between $5 and $11 million in additional revenue per aircraft. The bedroom in the ceiling pays for itself many times over. That revenue is also what makes the longest flights on Earth legally possible. A 17.5-hour nonstop legally requires 4 pilots, 2 at the controls at all times, 2 resting in rotation. Without the overhead module, the off-duty pilots would need main deck seats or lower lobe bunks, consuming the revenue that justifies the route. When Boeing first proposed putting crew members into the crown of the 777, the FAA had no existing rules for sleeping humans suspended between the cabin and the outer skin. The agency had to write entirely new safety requirements from scratch. The bedroom didn't just solve a fatigue problem, it created an entire category of nonstop flight that couldn't exist without it. On the Boeing 787, the crew rest crossed a threshold most passengers would find hard to believe. The FAA certified it for occupancy during taxi, takeoff, and landing, phases of flight when every passenger must be belted in a cabin seat. Off-duty pilots on certain 787 operations can legally ride out takeoff strapped into crash-rated bunks inside the ceiling, rather than occupying a jump seat in the cockpit. The pod earned that approval by passing 9G dynamic sled testing, the same violent deceleration standard applied to the aircraft's passenger seats. A bedroom in the ceiling, certified to survive a crash. The next time you board a long-haul widebody and see a flight attendant disappear through an unmarked door near the galley, or notice a stretch of ceiling where the center bins should be but aren't, you're looking at the entrance to one of the most tightly engineered spaces on the aircraft. A composite pod 2/3 lighter than its aluminum equivalent, floating on vibration isolators, fed by its own humidified air supply, fitted with blowout panels designed to fail on command, and connected to the cabin below by a trapdoor hidden inside what looks like a broken luggage bin. 600 pounds of bedroom suspended directly above your head. Now you'll notice it every time. What's something on an airplane you've noticed but never been able to explain? Drop it in the comments.